Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series delivered for the BSc Physical Sciences students, and we are going through the paper on applied electronics, and in the unit 2 we have been discussing the very important phenomenon, namely the photoelectric effect, and the phenomenon of photoelectric effect was discussed in detail in the earlier lecture. So, the contents of this lecture are Einstein's theory of the photoelectric effect, Bohr atom model, Sommerfeld atom model, and vector atom model. And what is photoelectric effect? We have seen in the previous lecture the details and the laws of photoelectric effect, which was accidentally discovered by Hertz. Whenever a metal plate is exposed to some light radiation, electrons will be coming out. Electrons will not come out for all kinds of radiations. There is a critical frequency for which alone the electrons will be coming out. Anyway, this is a very simple picture which shows light beam which is incident on a metal plate, it is able to eject the electrons. Now, this is a phenomenon which was observed. How do you explain this phenomenon? Why should electrons come out? Why should electrons come out of the metal? Now, what about electrons? Electrons are quantum mechanical objects. However, people tried for a very long time to explain this phenomenon with the theories which were prevalent, which were the theories which were existing at that time. People tried to explain this phenomenon using Maxwell's electromagnetic theory. We have the wave theory of light. People tried to explain this or understand this phenomenon using Maxwell's electromagnetic theory of light. But the important point is, this phenomenon is an instantaneous phenomenon. This is very important. What do you mean instantaneous phenomenon? You have got a metal plate, when light is incident, immediately the electrons are coming out. When light is incident, the electrons are coming out immediately. There is no time delay. If one were to make use of Maxwell's famous electromagnetic theory of light, then there will be a time lag. There will be a lot of considerable time will be taken for the electrons to gain energy and to come out of the metal. Therefore, the photoelectric effect is an important phenomenon in the development of atomic physics for a simple reason. This effect shows that the famous Maxwell's wave theory of light is incompetent. Maxwell's electromagnetic theory of light fails. The wave theory of light cannot be used to explain this phenomenon. What is light? Whether light is a wave or a particle. It was Max Planck who developed what is called the quantum theory of light. What do you mean by quantum theory of light? Light consists of particles. It is said light is made up of waves. We have seen Fresnel, Young, and very many people who talked about wave theory of light. The Young's double slit experiment. You all know that the interference phenomenon, diffraction, polarization, so many phenomena can be explained only by assuming light to be made up of waves. You young students, I should pose the question, I have got a light source here, whether the light beam that is coming to my eyes, is it coming in the form of waves or rays or particles. You have studied dual nature of light. So, as on today you should know light has dual nature. So, light has both wave-like aspects. There are certain phenomena like interference, polarization, diffraction, which demand light radiation to be treated as waves. This is a particular phenomenon wherein the wave theory fails. This is a photoelectric effect assumes considerable significance. Who explained the photoelectric effect? The photoelectric effect was explained by Einstein. Even though Albert Einstein is well known for very many things, right? He is the father of laser, he is known for the special theory of relativity, which gave rise to the atom bomb, right. What is the significance of, I used to ask my young students, what is the significance of the special theory of relativity? It gave rise to the atom bomb, variation of mass of the particle with velocity and so on, the energy mass relation, you have E is equal to mc square. Now, this comes from special theory of relativity given by Einstein, but Einstein many people do not remember or wrongly assume Einstein is given the Nobel Prize for his theory of relativity. It is not true. Einstein is given the Nobel Prize for explaining the simple, even though I will call simple, it is the photoelectric effect, for explaining this. Now, what is the kind of thing? What did it do? He is the first person to make use of Max Planck's quantum concepts, right. The important point is the quantum theory was used in atomic physics for the first time by Albert Einstein. It is Albert Einstein used the well known Max Planck's quantum theory. Where was the quantum theory used? You know the black body radiation, you know the Rayleigh-Jeans law, you know the Wehr's law, you know the Max Planck's interpolation formula, which holds good for the longer wavelength and shorter wavelengths in the radiation coming from black body. Okay, black body radiation can be explained, the whole spectrum can be explained from Planck's quantum theory. That quantum theory was used for the first time in atomic physics, first time for a material science problem. It is a material science problem wherein you have a metal exposed to light, electrons are coming out. The first instance when the quantum theory of light radiation, the fact that light consists of photons, it was invoked to explain a material science problem, right, for which rightly Albert Einstein was given the Nobel Prize. For a simple reason, the equation which I am going to show will be looking very simple, very trivial, but nevertheless the importance lies in the fact that it is the first instance when the radiation is treated in terms of photons to explain the ejection of electrons, right, ejection of electrons. Now, this particular thing you should be able to correlate with the lectures, lecture I gave sometime in the previous lecture. Okay, you have the photoelectric effect, light is incident on a metal plate, electrons are coming out. You treat the light beam as made up of photons, and you all know by now every student knows, even in high school you write E is equal to h nu. If light of frequency nu, the light radiation, any radiation, the radiation may be X radiation or ultraviolet or gamma radiation, whatever be the radiation, this equation holds good. What is the equation? The left hand side E refers to energy of the photon, that will be Planck's constant times, which is the well known constant, the most fundamental constant. It has got a minimum value in the whole of atomic physics, the Planck's constant multiplied by the frequency of the radiation. The frequency of the radiation means radiation may be any radiation, it may be X radiation, gamma radiation, ultraviolet or infrared, whatever be the radiation, or radio communicate wireless waves, okay, any radiation. Let me try to explain the Einstein's photoelectric equation. He assumed the particle nature of light, the first point. I told you he is the first person to make use of Max Planck's quantum theory, which shows that light is made up of photons, right. Till then the electromagnetic theory, the wave theory of light given by Maxwell. Prior to Maxwell, we had other people also spoke about wave theory. The electromagnetic theory, I told you in the last lecture, it is impossible for the electromagnetic wave theory to explain the instantaneous phenomenon that is observed here, the ejection of electrons when the light is incident on the metal plate. It is an instantaneous phenomenon. This instantaneous phenomenon cannot be explained on the basis of wave theory given by James Clerk Maxwell. So, we go to the quantum theory. According to Max Planck, light consists of photons. So, the Planck's quantum theory was used by Einstein to explain this phenomenon. What is the phenomenon? The electrons in a metal are coming out of the metal when they are exposed to light radiation. Now, what about electrons? What are the electrons doing in metals? You know, metals have free electrons, and the free electrons will be moving with all possible velocities, something like gas molecules moving with different velocities in a gas. You take a gas, you know, according to kinetic theory of gases, the molecules will be traveling with velocities C1, C2, C3 and so on. You talk of mean free path and then the mean square velocity, using which you obtain the expression for pressure, P is equal to 1 by 3 m c square bar. What is c square bar? It is a mean square velocity. Similarly, here also people thought, of course, one should believe, why should the electrons should obviously be traveling with different velocities, right. The electrons will be traveling with different velocities, and then there is a principle called the Pauli exclusion principle. You can take classical objects. I can have this kind of object here, I can have in the table, I can have 10 objects, or I can have pad here, I can have 20 pads on the table, there are classical particles, or 20 chalk pieces I can have in a table. There is nothing which is preventing me having 20 balls or 20 chalk pieces on a table. On the table you got all of them will have the same energy, but when you go to electrons, there are certain rules. There is a specific rule given by Pauli, it is called Pauli exclusion principle, which says that you can have only 2 electrons at a particular energy level. You can have, so you cannot have 10 electrons in an energy level. Supposing you got 10 electrons, you can have 2 in the first level, 2 in the second level, 2 in the third level and so on. If you have got 10 electrons, you require at least 5 energy levels, and the topmost energy level is called the Fermi energy, right. It is called the Fermi energy, the topmost energy, and out of the total energy, kinetic energy, out of the total energy h nu that is possessed by the photon, part of it will be used to extricate the electron. The outermost, what is phi? Phi is the work function. Let me stop for a moment. When I am talking about work function, we will come back to work function at the break. Welcome back at a break. Now, we are trying to understand the phenomenon of photoelectric effect. I told you in the lecture before the break, the wave theory of light as given by Maxwell. You have heard of Maxwell's electromagnetic theory of light, the wave theory of light. It is incapable of explaining, it is not capable of explaining the photoelectric effect, which is the instantaneous phenomenon. So, this instantaneous phenomenon was explained by Albert Einstein, who was the first person to make use of quantum theory of radiation. So, the radiation according to Max Planck, the person who gave the quantum theory of radiation, the quantum theory was proposed by Max Planck in 1901. So, according to Max Planck, radiation consists of photons. So, the idea that the light that is incident here consists of photons was made use of Albert Einstein to explain this phenomenon. So, if light is incident on a metal plate, I told you that the electrons which you have in a metal, all of them cannot be found in the same energy level. If you have got 10 electrons, we have the Pauli principle, which leaves restrictions on the number of electrons you can have in a particular energy level. In a particular energy level, only you can have 2 electrons. I will come into the details later after going through the atom models, which I will be dealing with in the lectures to come. So, the Pauli principle, which is to be made use of when you are talking about electrons, you can have at the maximum only 2 electrons in a particular energy level. For the electrons moving in a metal or a semiconductor in a energy level, you can have only 2 electrons. Therefore, if you got 10 electrons, you require at least obviously 5 energy levels, and the 5th energy level is given the name Fermi energy. Okay. Now, you got electrons here up to some value here. Okay. You got electrons here up to this energy, that energy may be the Fermi energy, that energy should be the Fermi energy, and then by shining light the electron is coming out, right. Now, the difference between this energy and the vacuum level is known as the work function. When you want to take water from a well, you have to do work, because it is a gravitational potential. Water in a well will not be coming out of its own, water will not be coming out, right. You have to put a bucket and you have to do some work to take the water out. Similarly, if you go to the hydrogen atom, you have to spend some energy to remove the electron. How much energy is required to remove the electron from hydrogen atom? You all know that 13.6 electron volt is the energy that should be supplied to remove the electron from the hydrogen atom, or to ionize the hydrogen atom you require 13.6 electron volt. That much energy should be supplied to the hydrogen atom in order that the electron is removed. Similarly, now the question is how much energy should be supplied to the electrons in a metal to remove them. To remove them means to remove which electrons? The electrons in the outermost orbits in atoms, and similarly the outermost energy, the topmost energy, that is the energy that the electron you got here, that is the topmost energy. There are the electrons which will be the lower levels will be here, this is the topmost level, and you are shining light, the electron will be coming out. The topmost level is the Fermi level, and the difference energy between the Fermi energy and the vacuum level is called the work function. What is work function? The energy difference between the vacuum level and the Fermi energy, that is called the work function. What is work function? That is the energy that should be supplied to the metal or supplied to the electron to remove the electron. It is called work function, means the work that should be done to extricate the electron or the electron to be ejected out of the metal. The electrons are held by the metal. The electrons will not be coming out of their own. Water will not come out of the well, right, the gravitational potential. Nucleon will not be coming out of the nucleus. You have to break, you have to give energy to split the nucleus, to the nucleons to be coming out. The electrons to come out of the metal, you have to give energy, and the energy required to remove the electron is called a work function. Okay, that is the work. What is the work function? H nu naught is the work function, right? This is the work function. You have phi here, phi in terms of frequency will be H nu naught. What is nu naught? What is nu naught? I told you in the last lecture, it is a critical frequency, right. The H nu is what? H nu is the energy. The critical energy that should be supplied to the electron in any given metal, in order that the electron is made to come out of the metal, the minimum energy with the 0 kinetic energy, that is your H nu naught, right. That is the work function, that is the phi, the work function, and therefore, E kinetic will be equal to H nu naught will be coming here. What is H nu? It is the energy given by the photon to the electron. H nu is the total energy, out of which H nu naught is the energy required to remove the electron. The remaining energy will be coming out as the kinetic energy, right. I think I will come to that explanation. I mean, as time goes on, once again the minimum energy required to remove the electron from a metal is H nu naught. What is H nu naught? The Planck's constant multiplied by nu naught. What is nu naught? It is a critical frequency, it is a threshold frequency, and it depends upon the nature of the metal. I told you cesium exposed to sunlight will give out electrons, right. Any light radiation will be able to eject electrons in a cesium plate. If the frequency of the incident light is just equal to the threshold frequency, the kinetic energy will be 0, right. The velocity will be 0. Just the energy required to remove the electron. The electron will come out of the metal and will come to the surface of the metal, and if the frequency incident light is greater, what will happen? The electron will be able to come out of the metal and again will come out with a fairly high amount of velocity or an associated kinetic energy. Therefore, if nu is greater than nu naught, then the difference in energy H nu minus H nu naught is used in giving kinetic energy to the electron. Therefore, you write, if the mass of the electron is m, the velocity is v, then H nu minus H nu naught is equal to half m v square. So, this is the relation which was given by Einstein, which got him the Nobel Prize. You see Einstein here, and the Alfred Nobel initiated the award of Nobel Prizes. So, Einstein got the Nobel Prize for giving an equation of this kind. What is the meaning of this equation? It is the equation, you can also try to write an equation of this kind. What do you have here? I have H nu. What is H nu? It is the energy of the incident photon. If I have a photon with energy 8 electron volt, right, 8 electron volt, then the work, what is the work function for potassium? For potassium, I told you in the last lecture, is 2 electron volt. To remove the electron from the metal, the energy required is 2 electron volt. You give 8 electron volt, the energy spent to remove the electron is 2, then what is the remaining energy? It is 6, 8 minus 2 is 6, right. So, you have here 8 minus 2 is equal to 6. I think this equation you can also write. So, what Einstein did is he wrote 8 minus 2 is equal to 6. What is 8? 8 is the energy of the photon, the incoming photon is say 8 eV, out of which H nu naught is what? It is a work function, the energy required to remove the electron from the metal out of 8 electron volt, 2 electron volt is the energy required to remove the electron from the metal. So, 8 minus 2 will be 6, out of total energy 8, 2 is spent to remove the electron. Obviously, the removed electron, the electron will take the remaining energy. So, it comes out with the kinetic energy, namely 6 electron volt. Therefore, what Einstein wrote is 8 minus 2 is equal to 6. Therefore, what I would like to tell you is, you can also write an equation 7 minus 5 is equal to 2 or 4 minus 2 is equal to 2 and get a Nobel Prize, right. So, the important point is, it is a human mind. The credit goes to Einstein, as he was the first person to apply the ideas given by Max Planck, or the quantum theory of radiation. Light consists of photons, was made use of by Einstein for solving a material science problem or in atomic physics for the first time. So, that made him to win the Nobel Prize. Not only that, this equation or Einstein's explanation shows the death of the Maxwell's electromagnetic theory of light. That means, the wave theory of light cannot be will not be able to explain all the phenomena. Maybe I will tell you the Raman effect, the Compton Raman effect. Again, what is the Raman effect? There again you consider the radiation, light radiation is not being considered at all times of waves. You have studied the light consists of waves, right. The interference, diffraction, polarization, they are explaining, assuming light to be made up of waves. But here is a phenomenon where light should be considered as though it is made up of photons. So, the quantum theory of radiation, that is considering light to be made up of radiation, I mean photons, that is important to explain the photoelectric effect. Not only photoelectric effect, the Raman effect, Compton effect, so many other phenomena which came to light later. These experimental findings can be explained only on the basis of quantum theory of radiation, which was used first time in atomic physics by Einstein. That is the reason why he was given the Nobel Prize. The equation, well, again I will tell you, the youngsters, the equation is very simple. The equation says 8 minus 6 is equal to 2. Okay, 2 is or 8 minus 2, 2 is what? The work function for potassium. 8 minus 2 is equal to 6. This you can also try, but the important thing is the human brain, that is, you have to apply a particular proper thing at for a proper effect, right. Let me now pass on to the summary of this lecture. The photoelectric effect could not be explained on the basis of electromagnetic theory of light. Einstein was the first person to introduce quantum theory of light to explain the material science problem, even though the equation is so very simple. Let me now pose a few questions to you with regard to this lecture. Question number 1, explain Einstein's photoelectric equation. Question number 2, what is meant by critical frequency. With this we come to the end of the lectures on photoelectric effect, and in the lectures to come we will see the atom models. Thank you.